Hello everyone, this is the Space Channel. These days, almost everyone has heard of black holes, and science fiction uses them actively. Still, as recently as 60 years ago, most scientists believed that black holes did not exist, and that similar objects appearing in calculations were the result of researchers' mistakes. The idea was that there must be some unknown laws of nature that would prevent black holes from forming. So let's sort out together how scientists came to conclude that black holes really do exist. The history of the idea of black holes, or more precisely, of black stars, begins at the end of the 18th century. At that time, nobody yet knew about wave-particle duality, and light was considered to be certain particles of a substance called ether. In the year 17, the English astronomer John Michell, viewing light through the lens of Newtonian mechanics, and treating it as massive particles, constructed a relatively simple chain of reasoning. If we throw a stone upward at a certain speed, it can travel some distance from Earth, then pause for a moment, and fall back to Earth. The greater the speed with which we throw this stone, the higher it will rise, all the way up to the escape velocity, at which the stone can fly away from Earth entirely. Since, in Michel's thinking, particles of light were identical to that stone and were likewise subject to the influence of gravity, they should behave analogously. That is, when a star emitted a particle of light, this particle would fly away from the star, gradually slowing under the pull of gravity until it stopped, after which it would fall back onto the star. Thus, the radiation from a star could be seen only within a specific neighborhood around the star, the region it could reach. In contrast, at great distances the star would be invisible because its light would simply not get there, turning back before reaching the observer. Moreover, the star's region of visibility would not depend at all on its brightness. Such stars could be even trillions of times brighter than the sun. Only their mass and size would determine how far they would be visible. Therefore, these invisible stars were called black stars, and in many sources, you can also find the name dark stars. Michel carried out calculations and determined that light would never be able to escape a star with the same average density as the sun and a radius 500 times that of the sun. In addition, he calculated the size to which the sun would have to be compressed so that light could not escape from its surface. That is, it would be invisible to everyone outside it. He obtained a radius of about 3 kilometers. This number is exciting, because today we already know that a black hole with the mass of the sun must indeed have such a radius. 13 years after Michel, the French mathematician and astronomer Pierre-Simon Laplace proposed a similar idea. Whether he did this independently or under Michel's influence is fundamentally unknown, but it is considered that he worked independently. His calculations produced identical results, though they were more mathematically rigorous. However, the idea of black stars was included only in the first 2 editions of his book, Exposition of the System of the World, published in 1696 and 1699, and was removed in subsequent editions. No one knows the exact reasons. Perhaps it was because the idea seemed fantastical to everyone. Probably because new research on the invariance of stellar aberration across different stars contradicted his conclusions. But most likely it was because just a few years later, at the very beginning of the 19th century, the wave theory of light burst into prominence, which undermined the entire principle of stars not letting light go and rendered this idea meaningless. After that, the concept of black stars or black holes faded into the shadows for 100 years. Scientists returned to it at the beginning of the 20th century, when there were still 50 years before the first use of the term black hole. This happened after the appearance of the general theory of relativity at the end of 1915 and its broad acceptance over the next few years. It was precisely this theory that predicted that regions of the universe could exist with such significant curvature of spacetime that even light would be unable to leave them. The first to move in this direction was the German Carl Schwarzschild, one of the most talented astrophysicists of the time. At that moment, He was serving in the German army and was fighting with the Moscow Horde on the Eastern Front. Having read Einstein's report in the Bulletin of the Prussian Academy of Sciences, he immediately set to work on investigating what the general theory of relativity predicts for stars, and within a few days, he derived a solution for the curvature of spacetime outside an idealized star, which was presented by Albert Einstein to the world in January 1916. A few weeks later, he obtained solutions for what lies inside the star. Unfortunately, after 4 months, Schwarzschild died from an illness he had contracted at the front. He did not live to fully reveal his talent and complete his research, but his work was continued, and today the geometry that describes the curvature of spacetime near and inside idealized spherical objects bears his name. Over the next few years, Schwarzschild geometry became widely used among physicists and astrophysicists, and everyone agreed with its predictions regarding ordinary stars. However, no one took seriously the prediction that extremely massive stars with minimal radii could become black holes. In the 1920s of the 20th century, the most respected astrophysicists, among whom were Arthur Eddington and even Einstein himself, refused to acknowledge that such objects could exist. Black holes simply contradicted their intuitive understanding of the world, and the scientists groundlessly rejected their existence, offering arguments along the lines of, "These objects smell bad," or "there must exist laws of nature that prevent a star from turning into a black hole." In fact, these personal, unfounded convictions of the mastodons of the science of that time, that black holes are unnatural and should not exist in the universe, seriously slowed research. They really did try to support their thoughts with calculations. Still, because of their personal convictions, they interpreted those calculations in favor of the absence of black holes in nature. In reality, the results could also be interpreted in the opposite direction. In 1939, Einstein published a paper denying the existence of black holes. If we simplify its content as much as possible, Einstein's idea can be described as follows. As a star compresses, the gravitational force at its surface increases. To maintain a stable star, the particles at its surface must move at ever higher speeds so they do not fall inward. When the size of the star decreases to 1 1/2 times the critical radius, that is, the radius at which an object becomes a black hole, the speed of the particles on the star's surface must equal the speed of light, and further compression becomes impossible, because it is impossible to exceed the speed of light. To a modern physicist, one thing immediately stands out. Einstein made an unjustified assumption that the star must remain stable and that the particles must not fall inward. Why should they not, at speeds less than the speed of light, simply fall inside and form a black hole? Another of Einstein's arguments can be formulated like this. As the star is compressed, the pressure in its depths will rise, and when the star's radius is at 1.125 times the critical radius, the pressure in the core will become infinitely large. And since no real substance can generate infinite pressure, it is impossible to compress anything to such a size, and black holes cannot exist, because to form them, one must compress the star even further. Here again, a logical error creeps in. Einstein assumed that there must be interactions that would lead to an infinite increase in pressure, but in reality, such interactions do not exist. The pressure will increase only up to a specific limit, and then everything will collapse. In fact, Einstein's results can be interpreted in different ways. After a certain threshold of compression, nothing will be able to generate forces that would stop a star from collapsing into a black hole. Nevertheless, scientists kept searching for such forces for a very long time, which helped them make a great many interesting discoveries. The first was the understanding of white dwarfs. Trying, so to speak, to stop a star from collapsing into a black hole, scientists turned precisely to them. A theory was developed that describes the structure of white dwarfs. According to it, the pressure in the cores of white dwarfs, which keeps these stars in a stable state, is not caused by the thermal motion of particles, as was previously believed, but by the degenerate motion of electrons. Kip Thorne describes this motion by comparing it to human claustrophobia. When matter is compressed as intensely as in a white dwarf, the electrons are confined in extraordinarily tight cells. Since they are simultaneously particles and waves, this leads to a substantial shortening of their wavelength, an increase in their frequency, and, consequently, an increase in their energy. The electrons begin to dart frantically in their cells, creating tremendous pressure that does not decrease as the white dwarf cools. In this way, a force arises that, even as the star cools and thermal pressure decreases, does not allow it to collapse into a black hole. It would seem the solution had been found. The collapse of stars into black holes was stopped. They simply become white dwarfs, slowly cool, and remain in the universe as chunks of rock. Scientists should have been satisfied. But the young scientist Subramanian Chandrasekhar discovered an upper limit to the mass of a white dwarf, beyond which the pressure of a degenerate electron gas can no longer halt the collapse. He presented his discovery at a meeting of the Royal Astronomical Society in London, where he was roundly criticized by his colleague and friend Arthur Eddington, one of the most authoritative astrophysicists of that time. Eddington directly called Chandrasekhar's mathematical approach a reductio ad absurdum of the formulas of relativistic degeneracy, and declared that there must exist laws that would not allow a star to behave so absurdly, namely, to collapse into a black hole. These words considerably slowed the development of the idea of black holes, because most astronomers blindly trusted Eddington's authority. Chandrasekhar, for his part, was deeply hurt by this situation. For 1/4 of a century, he set aside his research on white dwarfs and worked in other areas of astrophysics. Yet in less than 10 years, the scientific community recognized that Eddington had been wrong, and that Chandrasekhar's calculations were correct. At the same time, strangely enough, Chandrasekhar and Eddington continued to maintain warm relations thereafter. Nevertheless, scientists still resisted the idea that black holes could arise in the universe. Most astronomers believed that before dying, a star ejects matter into interstellar space, so much, in fact, that the remnant never exceeds the Chandrasekhar limit. But this was not so. The second great discovery was neutron stars. Fritz Zwicky of the California Institute of Technology predicted that if a star is too massive to become a white dwarf, it can, upon its death, form a neutron star. He made this discovery together with the astronomer Walter Baade. They worked together for many years and, at the Mount Wilson Observatory, observed extraordinarily bright novae, which they themselves named supernovae. In attempting to explain the energy source of these explosions, Zwicky concluded that about 10% of the mass of a star's core, when collapsing into a neutron star, is converted into the energy of the explosion. At the same time, Zwicky had the reputation of being the local clown, and in assessing his works, both then and now, scientists come to the conclusion that they contain a heap of gaps, many points with insufficient argumentation, or none at all. How he managed to describe neutron stars so accurately with such a fragile approach remains a mystery. Most likely, it was the role of this person's brilliant physical intuition. Zwicky and Baade published their research in the 1930s. Still, observational confirmations of the existence of neutron stars and models of their structure appeared only at the end of the 1960s. Indeed, 20 years later. It would seem that once again everything was fine. The universe was saved from black holes, massive stars simply became neutron stars, cooled down, and remained as chunks of rock. However, this was not the case again. The work on neutron stars was enormous and exciting. Still, in the context of this video, the following is essential. Neutron stars, just like white dwarfs, are supported in a stable state by the pressure of a degenerate gas, now a neutron gas. Two physicists from the California Institute of Technology, Oppenheimer and Volkoff, discovered for neutron stars, just as for white dwarfs, a limit beyond which compression can no longer be halted, and they will collapse into a black hole. In fact, it was Oppenheimer and his team who first calculated what would later be called a black hole. They did this roughly for highly idealized stars and most likely planned to continue their work. But the Second World War intervened. Most scientists focused on the military sphere. Oppenheimer headed the Manhattan Project to develop the American atomic bomb, and research on black holes almost stopped for more than 10 years. Since, after the war, most scientists continued working on the development of thermonuclear weapons. But in the 1950s, all the forces, knowledge, and resources that Oppenheimer had gained during his work on nuclear weapons were thrown into the study of black holes. His team quickly developed a description of what would later be called a black hole. But the main thing is that after decades of disputes and rejection of black holes as a phenomenon, they began to enter the scientific community actively and to be studied, capturing the attention of a tremendous number of scientists. In fact, by the end of the 1950s and the beginning of the 1960s, scientists accepted the concept that massive stars at the end of their lives compress, and that nothing in nature can stop this compression. In 1967, John Archibald Wheeler first used the term black hole when describing their properties. This term pleased physicists and very quickly came into general use. Beginning with the 1960s, black holes became a full-fledged class of objects studied on a par with any others, and the golden age of black hole research began. That is precisely how scientists arrived at this concept. If you are interested in hearing more details about how ideas about black holes have developed from then to the present, write about it in the comments, and we will make a separate video on this topic. That's all for now. If you enjoyed the video, please give it a like and subscribe to the channel. See you next time.